Okay, so today in class we finished the front of this sort of guided note-taking sheet on exponential functions. And I want to pick up where we left off with part C, or equation C. And I'm going to put this into my calculator to do the table real quick. If you don't have a calculator like this that does the table, you can do the table by hand. Let's see, we've got 3 times 1/2, oops, 3 times 1/2 to the x power. Remember, the x is next to 4. Right arrow a couple times to get out of the exponent, and then it's -2. Now, before I even write down my table of values, I'm going to take that -2 into account and point out that because of that -2, we have a vertical shift, and that tells me where my asymptote is going to move. My asymptote is going to move from y equals 0 down to y equals -2. And I'm going to go ahead and draw the asymptote because it's helpful to have it in place before you start plotting points so that you make sure you don't accidentally go over the asymptote. We can't cross it. All right, I'm going to do the same points we were using on the other ones. We've got -2, 10, -1, 4, 0, 1, 1, -1/2, and 2, -5/4. Now let me point something out about this. We talked about how exponentials and geometric sequences are very closely related, and that all geometric sequences would make an exponential graph. If we graphed the geometric sequence, it would be an exponential function, and it would look like other exponential functions. But let me point out here, this is not a geometric sequence. There's no number I can multiply 10 times to get 4, and 4 times to get 1, and 1 time to get -1/2. That would not have a common ratio. The reason for that is the vertical shift. The vertical shift is what makes this look different from your basic geometric sequence. Remember, geometric sequence has this equation. There's no plus or minus anything in the back. There's no room for a vertical shift there. There's no place to account for that. So if we have a vertical shift, then the equation no longer fits this format. Whereas if you look at D, when we look at D, we should get something that's a geometric sequence because this has the same format. Okay, we have a number times a common ratio to a power. So that's just in case you were curious about that. That is why, in this case, it does not fit a geometric sequence exactly. If we remove the -2, it would. So -2, 10, -1, 4, 0, 1, 1, -1/2, and 2, -5/4. So I'm going to draw my curve. And it doesn't hurt if you want to draw some extra points over here to get a better idea of what that's going to do. All right, the domain for this and for all exponential functions is all real numbers, which means all the way from -infinity to +infinity. And notice that when we're writing things in interval notation, this tells me I have a range of values from -infinity to +infinity. We always use parentheses with infinity symbols, because the only other thing we would use would be brackets, and brackets fit if it can be equal to that. Well, you can't be equal to infinity. Infinity is not a destination. We can't arrive at that place. So we can't ever equal infinity, and so therefore we say just parentheses. The range here is going from -2 up, but it's not actually going to ever touch -2. So y is greater than -2. If this had been greater than or equal to, I might use a bracket, or I would use a bracket with -2. But as it is, it's just greater than, so I use parentheses. So on these, you would always use parentheses for your interval notation because it's never going to touch the asymptote. Also, another thing to notice here, well, actually, we're going to talk about it right here. The end behavior says as x is approaching -infinity, that means on the left. As x approaches -infinity on the left, this is going toward +infinity. On the right, it's going toward -2. Okay? So what we have here is always one side of my graph is going to be approaching the asymptote. The other side of my graph is always going to be approaching either positive or negative infinity. It's not always the left that goes up and the right that goes toward the asymptote. It can be the other way around. But for your end behavior, one side will always approach whatever the value of the asymptote is, and the other side will approach positive or negative infinity. All right, next we have y equals -4 times 2 to the x minus 3. That x minus 3 makes things a little different here because it actually indicates a horizontal shift. That -3 is inside the function, so to speak. But on the table, we still just put it in. -4 times 2 to the x minus 3 power. If you have a calculator that doesn't work this way, where it actually raises the exponent up higher than the other numbers, you would want to make sure you put x minus 3 in parentheses to show all of that is up in the exponent. Okay, I'm going to make the same type of table over here. This one I actually might extend a little bit, and I may have to finish this in a little bit. This is -1/8, -1/4, -1/2, -1, -2. This one is geometric because there's no vertical shift. So that's why I'm extending it a little bit to get this nice and accurate. Kind of hard to be accurate between 0 and 1. But here's what it starts looking like after that. I'm going to keep going. You're going to hear some noise here. Oh, let me draw my asymptote. It's at y equals 0. The domain, as always, is all real numbers. And the range here is y is less than 0. So that means from negative infinity to 0. On this one, on the left, it's approaching 0, and on the right, it's approaching negative infinity. Okay, this last part may be the most useful thing on here for you. This is basically just looking at the basic shapes. There are 4 ways an exponential function could look. 4 basic shapes in terms of the curve. Remember that this is the basic format. That's what these A and B's are. Since there's 4 ways they could look, you might notice that I've given you 4 graphs here. All the other ones on here. Okay, so what you're going to do is you're going to look at each one of these and find the graph that matches that and see what the basic shape is. For instance, on the first one here, the A value is 2. That's positive. The B value is 3. That's greater than 1. Okay, positive A, B greater than 1 has the shape that we had right here, which is like this, basically. It doesn't have to be terribly accurate. You're just getting an overall idea of what the curve would look like, because there are 4 different ways that an exponential curve could look. So go ahead and look at B, C, and D and figure out where each one of those shapes would fit. And then do the homework here, and we will go over it on Monday.